Hello ladies and gentlemen. Well, today we're going to have a look at kinematics, which is a study of motion. We're going to specifically look at position, velocity and acceleration. Okay, so let's go. We're studying motion in a straight line only, so fear not, it'll be okay. Such motion is called rectilinear motion. Even though a body in motion can be large or small, we will consider that all forces which cause the motion which act on the body are acting through a single point, e.g. the centre of gravity of that body. Okay, now we won't use that information at all really about the forces because we're just considering the motion. Okay, we're just considering the motion and not the forces which cause the motion, but in all cases we will be acting on the bodies through their centre of gravity, if you like. Alright, it's very important to distinguish between vector and scalar quantities when studying motion. Yes, it is. Displacement, velocity and acceleration are all vector quantities, which means they have both a magnitude and a direction. That's what a vector is, guys. Distance, speed and time, on the other hand, are scalar quantities, which means that they only have a magnitude, okay? They only have a magnitude. So there you go. Because we're considering motion in only one direction or one dimension, that is forwards or backwards, or if you like up or down, we will denote the direction as plus or minus, where plus is a predefined direction. E.g., motion to the right will be defined as positive direction and motion to the left will be defined as negative direction, as on a number line. You know that, don't you? Okay, let's go. We'll have a look at position. Now, position is the location of a body relative to the origin in all of the study that we will do. Positions to the right of the origin will be positive and positions to the left of the origin will be negative, just as you have on a number line. Have a look at this. Now, okay, that's pretty easy, isn't it? Intuitive, that's the origin. That position relative to the origin is plus 2, okay? This position relative to the origin is negative 3. Okay, very easy because you know about number lines. Now displacement, now that we've got position sorted out, let's have a look at displacement. Displacement is defined as the change in position relative to the origin for any given journey without any consideration at all of what happens during the journey. Okay, so I'll demonstrate that in a moment. So if a path begins at x equals 3 and ends at x equals negative 5, then the displacement is just the destination position minus the starting position. That's all it is, and you don't care about the journey in between. You don't care about any meandering, wobbling around, going all over the place. You don't care. It's just the destination position minus the starting position. Just like a vector, okay? Just like a vector. You only care about where you ended up compared to where you started. So for that particular case that I just gave you there, it'll be destination position negative 5, take away, minus, subtract the starting position, which was plus 3, which will get you minus 8. Displacement for that particular journey, alright? Negative 8 units, or 8 units to the left. Now, as we were saying, it is important to distinguish between a scalar quantity such as distance and a vector quantity such as displacement. That's very important. E.g., consider the following journey in which they become different. Okay, they become different because the particle changes direction. If the particle changes direction, then the distance is no longer the same as the displacement. So let's have a look at this. I'll illustrate the point for you. We're starting at the origin. We go to positive 8 and then we decide we need to turn around and we go back to negative 3. Okay, so what is the distance and what is the displacement? Well, the distance travelled is 8 units to the right and then, if you work it out, 11 units to the left. Now we don't care about the plus or the minus in distance, it's just the length of the journey. So it's 8 units, don't care about right or left, plus 11 units, don't care about right or left, gives you a total of 19 units. That's what we mean by a scalar. It just has a magnitude. There's no direction anywhere considered in distance, alright? However, the displacement on the other hand is, now we've got distance and direction. Finishing position is -3. Take away starting position, which was the origin, gets you -3 units. You see? We don't care about the journey, we just care about where we ended up compared to where we began. That is what displacement is, okay? There minus there, okay? That's it. See how they're different? Because the particle changed direction. If it all went in the same direction and never turned around at all, then the distance would be the same as the displacement. Yes, that has a magnitude only, that has a magnitude and a direction, because that one, that second one, that displacement is a vector, the distance is only a scalar. Magnitude, direction, yes? Are you getting this? Great. So yes, distance is simply the length of the journey, and displacement is the destination position minus the starting position, regardless of what happens in between. Goody. Now here's example 1. We've got 3 examples here for you today. Hooray. Example 1, a particle moves in a straight line so that its position at time t is given by x as a function of t, x bracket t equals t squared minus 5t plus 4. xt is measured in centimetres, that's the displacement or the position if you like, and t is measured in seconds. Alright, that's pretty standard stuff. Now, what do we have to find out, guys? The initial position, the position after 5 seconds, and the displacement during the first 5 seconds. Alright, that's, and the distance travelled during the first 5 seconds. Now that's going to be interesting because it's probably going to have changed direction. So don't fall into the trap. Don't fall into the trap. Let's have a look at it. We'll probably graph it, I think, just to have a look at the whole position versus time situation. So the initial position occurs when t equals 0, so therefore we'll sub t equals 0. This is part A. Therefore we get that, okay, and therefore we get plus 4. That's the initial position, okay, plus 4. Okay, part B, the position after 5 seconds. Well, we just plug in t as 5 into that, and what do we get? Aha! Does that look right to you? I think so. So that'll be plus 4. My goodness, they're both the same. Position. Well, that's interesting. What about part C? The displacement. Alright, well, you know what to do there. Okay, during the first 5 seconds, it's just the position at 5 seconds minus the position at 0 seconds, and we just work them out above in part A and B. So that's 4 minus 4, which means no displacement. I know, it seems wrong, doesn't it? But that's the way displacement works, okay? So, fear not, it's alright. Part D. The distance travelled. Alright, now this is where you've got to be careful, guys. The distance travelled, that's a scalar, okay? And if it's turned around during its journey, gone back the other direction, as it were, then we have to work out the 2 components of the journey and then add up the distances for each. Okay, a graph? Yes, a graph. Please, let's have a graph. Well, it's a quadratic, isn't it? Yes, it's a quadratic. It's this thing up here. Okay, so x is on the vertical, t is on the horizontal, to get ourselves sorted out here, orientated, and there is the graph. Alright, so we got there, we got the position when t was 0 was 4, we got the position when t was 5 was 4, and we've got these intercepts if you care to work them out, and I've actually worked out the turning point. You know that for a quadratic, the turning point or the vertex is always halfway between the 2 intercepts, yes? So that would be at 2.5, yes? And I've worked it out for you. You'll just have to trust me on that, okay? Very interesting. Now, you tell me, you have a look at that and you tell me, did that particle change direction? Did it change direction? Well, the turning point, yes, is that point which I worked out for you, just writing that down, and you can see that basically it's going, as time progresses, the position is getting less and less and less and less and less and less. It's, in other words, it's going to the left. Now it's to the left of the origin now, okay, into the negative. Now it gets down to there, that position there, minus 2.25 at 2.5 seconds, and now it starts coming back the other way. In other words, the x value is becoming more positive, it's travelling to the right. Now, can you get that interpretation? It's very crucially important that you do. See, it's travelling to the left here, x is becoming negative, 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 more negative, more negative, just past the origin, minus 2¼ now it starts going back the other way. So it has changed direction, right? And it got back to the point where it started at 5 seconds compared to where it was at 0 seconds at the start, alright? See, do you get it? You've got to think about that. You've got to think about that and interpret that graph correctly. So it changed direction when t was 5/2. It did. Hence the distance is different from the displacement. Oh yes, it is. So we've got to work out the distance is the sum of is the distance from the start to the turning point plus from then the turning point to the ending point. Okay, the two components of the journey. This one to here and this one to here. Okay, and add them up. Don't worry about the plus or the minus because distance doesn't care about that. So I put modulus signs around this. Okay, that's the turning point position. Take away the starting position and just do the modulus of it, the absolute value of it. Then do the same thing, ending position minus turning point position, and they come out at 6¼ each, which gets us 12½. So that is the distance, and it's very, very different from the displacement, which was 0. Okay, now you're beginning to get this now. It's pretty fascinating, isn't it? It certainly is. Okay, what's this? Velocity. Velocity is the rate of change of position with respect to time. Okay, it's the rate of change of position with respect to time. We can consider two different versions of velocity. That is the average velocity and the instantaneous velocity. So let's have a look at those. The average velocity is simply just the change in the position over the change in time. The overall change in position over the overall change in time, alright? And that equals x2 at time 2 minus x1. That's the finishing position, that's the starting position, that's the finishing time, that's the starting time. So it's the change in position x2 minus x1 over the change in time t2 minus t1, alright? Now, that is the average velocity, right? The average velocity. If you had a graph of position versus time, you just select point 2 and select point 1 and you would draw a straight line and do the gradient, because that's what it would be, the gradient of that line between those 2 points, yes? Now on the other hand, instantaneous velocity is just dx by dt, which is the derivative, the derivative, the gradient at a point on the graph, the derivative of the position function with respect to time at a single point, at a single instant in time, hence the name instantaneous velocity. Okay, that's very different. Yes, that's what that is. Now, we give it this notation in kinematics. We call it x dot t as a function of t. That means the derivative of x with respect to t. That's the notation very commonly used in kinematics, so you better get used to that. Okay, and also, last but not least, average speed, guys. Average speed is just the total distance travelled in some particular time interval divided by that particular elapsed time that's occurred. Okay, that's what the average speed is. Alright? If they asked you for, by the way, I haven't put it here, but if they asked you for the instantaneous speed, it would just be the magnitude of the instantaneous velocity, okay? It wouldn't have a plus or a minus though, it would just be a number because it's a scalar. Yeah? Alright, now I think we're going well here. Units for velocity, well, typical units could be centimetres per second. Remember, it's distance over time, or displacement over time actually. Meters per second would be another one, kilometres per second, or maybe kilometres per hour. There's another way they notate it. They call that centimetres and then times second to the minus 1, similarly for that one and similarly for that one, yeah? Or even this one, centimetres dot sec to the minus 1, yeah? You get that, don't you? Yeah, okay, you just got to get used to the notations. Alright, here comes example 2. This is a velocity one now. Particle moves in a straight line so that its position at time t seconds is given by that same thing as we had before in example 1. X is measured in centimetres, all right. Find the initial velocity, and when and where the velocity is 0, the average velocity over the first 5 seconds, and the average speed over the first 5 seconds. Right, let's go. Very exciting. The initial velocity. All right, now, this is the position function. So to get the velocity function, what do we need to do? Yes, we need to get the derivative of the position function. Okay, so let's do that. So for that case, if x as a function of t is t squared minus 5t plus 4, you know how to do the derivative, don't you? 2t minus 5, okay? So therefore the initial velocity would be when t is 0, which if we plug 0 into this function up here, we'll just get that, which means we'll get minus 5 centimetres per second, alright? Minus 5, that means it's going at 5 centimetres per second to the left. Yes? Very excellent. Let's do B now. When and where the velocity is 0. Well, we know that that's what we've got to do. dx by dt equals 0. Therefore, 2t minus 5 equals 0. Therefore, t equals 5 over 2. That's ringing a bell, a very loud bell in my head, reminiscent of the previous graph that we did. Yes, because this example 2 uses the same position function as example 1. And do you remember where the turning point was in that graph? I do. I'll show you in a minute. Yes, also when t is 5 over 2, we've got the position there. We're working out the position. Yes? When and where, right? When and where. We got the when, it was 5 over 2 seconds. The where is minus 9 over 4 centimetres, or 9 over 4 centimetres to the left of the origin. Now, there it is, all summarised with Mr. Box. Thank you, Mr. Box, and a good job. So, yeah, that's got it done, hasn't it? Yes. NB, here comes the graph, guys. Here comes the graph. This can be seen from our earlier graph of x versus t. Dx by dt is 0. That's the stationary point. Yes, that's where the gradient of the x versus t graph equals 0, the stationary point. Yes? So for a quadratic function, this is the turning point, the vertex. Yes, there it was. You see? And we worked it out, didn't we, when we were interpreting the graph, that this is the point where it turned around. Yes? It got from this position here where x was 4 at t was 0, came down here negative, 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 and to there, that's the point where it turned around from going one way to going, that was to the left. This was the point here at which it stopped going to the left and started going to the right. So obviously, if it's going to stop going from the left and start going to the right, it's got to have a 0 velocity point at the instant when it converts from left-hand motion to right-hand direction motion, and that's the point there. That's where dx by dt equals 0. It's the turning point. You see? It all hangs together and it all makes sense. Yes? So this is the point when and where the velocity is 0. Okay? The when is 5 over 2 seconds. The where is minus 9 over 4 centimetres. It's mighty fine, isn't it? It is mighty fine. Okay, now what are we doing now? We want the average velocity over the first 5 seconds. All right, I think we can do that. That's simply the change in displacement over that time interval divided by the time interval itself. Okay. Now, as we worked out in the previous example, we worked out that they were both at 4 seconds. They were not 4 seconds, 4 centimetres. 4 centimetres. So 4 centimetres minus 4 centimetres divided by 5 seconds to get you a big fat 0. An average velocity of 0. Okay? That's what you get. Even though we know it moved, and oh yes, I know, it seems wrong. But look, for the average velocity, we only consider the displacement, the change in position, the destination minus the starting position, divided by the time interval which has elapsed. Okay, so we do get an average velocity of 0. There it goes. Now, the average speed will be quite different. So let's have a look at that now. For example 1, we did work out that the distance travelled over that first 5 seconds was 12.5 centimetres, so let's not work that out again. So therefore, the average speed, guys, will be the total distance divided by the total time, which is 12.5 over 5, which gets us 5 over 2, or 2.5 centimetres per second average. See, it's so different, isn't it? Because the thing changed direction. This is very different to that because the little beastie changed direction, changed its mind, yes? So, how do you like it? You have to be very, very, very careful not to mess this bit up here. Yeah, and you have to work out whether it's changed direction. And I recommend a graph to you every single time to work that out. Okay, acceleration now. Last cab off the rank. Acceleration is the rate of change of velocity with respect to time. The rate of change of velocity with respect to time. So just as we had velocity was the rate of change of position with respect to time, then we know also that acceleration is the rate of change of velocity with respect to time, okay? And we can consider the average acceleration and we can consider the instantaneous acceleration just in the same way as we did for velocity, the average and the instantaneous versions of. So the average acceleration is just the overall change in velocity over the overall change in time, or the time elapsed, which is that, okay, destination minus start over destination minus start, alright? And I'm just showing you that this can also be expressed as the dot, the x dot. V can be written as x dot, okay, as we do in kinematics, right? So just getting you used to that notation. Now, the instantaneous acceleration is just dv by dt, which is a derivative of the velocity function with respect to time. It is the instantaneous rate of change of velocity with respect to time, so it's the gradient at a point on the graph of the velocity time graph. The gradient at a single point in time will give you the instantaneous acceleration at that time. Okay, and we do these, we notate these with two dots, each dot denoting a derivative, so that's the second derivative of the position function, okay? Do you get that? Yes, very good. You could even call it v dot if you wanted to, v dot t. It's another way of doing it. See, do you get the idea? The derivative of velocity, or the second derivative of position. Okay, so acceleration is dv dt, which is the derivative d by dt of dx by dt. Did you get that? Yes, because v is dx by dt, okay, and therefore it's the second derivative of position with respect to time, okay, and it's all, yes, it's also called v dot t, it's also called x double dot t. Now, are you completely confused and going stark raving mad? No, 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 it'll be fine. You just got to get used to this notation. It's quite fun, so don't worry about it. Everything will be good. Okay, Mr. Box, thank you for your excellent work. Now, units for acceleration are, yes, it looks like, this looks like a bit crazy, doesn't it? Remember, it's the derivative of velocity with respect to time. So meters per second, every second, if you like. So change in meters per second with respect to time. Okay, so meters per second per second. They also call it meters per second squared and all kinds of crazy things. So no, I haven't got a speech impediment. It's meters per second, or centimeters per second, or meters per second squared, or centimeters per second squared, or meters dot second to the minus 2, or so on and so on. Yes? Okay, that's very good. Let's do example 3. And that'll be the end of it then. Now, this one I'm going to use some technology because the thing gets quite complicated. So please get your CAS device out and make sure you can do everything I'm going to show you on your CAS device. Okay. Particle moves in a straight line so that its position at time t seconds is given by x t equals t cubed. That's the same example. No, it isn't. It's everything multiplied by t compared to the previous example. I've just multiplied through by t. T cubed minus 5t squared plus 4t. X is measured in centimetres. Now, what are we doing here? Find the initial position, velocity and acceleration. All right, that's all right. And B, the times when it is instantaneously at rest and its position and acceleration at those times. Right, goody. Initial position, well, that's going to be easy peasy. There it goes, plug in t is 0, and away we go. So it just looks like it's going to be at 0. See, it's at the origin, guys. It's at the origin. So now we're doing the derivative of the displacement or the position function, and we get that. Have a look, make sure you agree. Now we're going to work out, what are we doing here? The initial velocity, so plug in t is 0, And there you go. It looks like it's doing 4 centimeters per second, or plus 4 centimeters per second, or 4 centimeters per second to the right. Yes, very good. Now we've got to do the initial acceleration. We have to take the derivative of the velocity function now, which gets us, have a look. There it is. So it's 6t minus 10, and we have to plug in. T is 0, don't we? We do. So there we get, yes we do. And so therefore it's minus 10 centimeters per second squared, okay? There we go. Or 10 centimeters per second every second to the left, instantaneously at t equals 0, yeah? Right, number B now. Now this is where it gets a little bit crazy, okay? Now the times when it is instantaneously at rest. At rest means the velocity is 0, okay? It's stationary, right? So let's do that. We're going to solve that for being equal to 0, okay? That's what we're doing. Now we better do a quadratic solution for that. Yes, because it's not working out very nicely for us. What do we get? Ugh, yuck. Yes, that's what I told you. It gets a bit mad. You can do some simplifying of that surd, because 52 is 4 times 13, so it'll be 2 root 13. Yes, now we can cancel through by 2. Aha, still pretty nasty. That's the times, the 2 times. Now, in case you're wondering, I did check that 5 minus root 13 over 3 is still positive, guys, because they have to be positive. You can't have negative time, can you? Definitely not, and at least not on planet Earth you can't. So, okay, we've got 2 times when the thing is stationary. That's them, okay? Now, that's the first part of part B. Now we've got to use our CAS device to work out, what are we going to work out? The times when it's instantaneous at rest. We've done that, and its position and acceleration of those times. Okay, the position, we have to plug these beastly looking times into this position function and into this acceleration function, alright, which is not very easy, so we'll do it on the CAS device. Please get it ready and make sure you can do this. We have a TI CAS handheld at our school, but if you have a Casio or something else like that, you just have to know how to do it on your device. But please make sure you can do it on your device. You have to get very, very good at using your CAS device. You do. Yes, too difficult by hand. Yes, I agree, Mr. Wolfman. Now, alright, so there's the first thing I've done on my CAS handheld device. I've plugged that function in. I've defined it as f1 of t, right? That's what I did. First thing, yes, that's x at t. Now, the next thing I did was the derivative, the straight derivative of that, and the CAS device has worked it out for me very nicely. That's x dot at t. Then I've solved it. I've done a solve statement, okay? No, please know how to do that. Please know how to do that. On the TI CAS handheld device, it's just menu, algebra, solve. It goes like that, and we get this, which is exactly what we got before. Okay, so we're up to where we got to before by hand, but from here on in we're going to do new things, because we can't be bothered doing any more of it by hand. So that's the times. Yeah, that's the times when x dot t, or the velocity, was 0, or the times when it was instantaneously at rest, aren't they? Alright, so now what I've worked out now is this is, remember that thing there is the f1 is the position function. So this is the position when at that time, that's the position at the other time. That's what you get. They're pretty ghastly, aren't they? So let's work them out. Yeah, I've worked them out as decimal versions. There they are, okay? On the TI handheld CAS device, you just do, what do you do? Control Enter. Yeah, Control Enter, which gets you the decimal versions. Okay, there they are. That is, yeah, the positions when the velocity equals 0. Okay, so what am I up to now? Now I'm doing the second derivative now. This is the acceleration function. So I'm working out what the acceleration function is there, 6t minus 10. We did do that before, didn't we, by hand? Now I'm storing the acceleration function as f2 of t. There it is, okay? And now what I'm doing here is I'm working out the value of the acceleration at this time here. That's one of those times, and that comes out to be that in exact value and that in decimal value there, okay? And that's just a restatement or a repeat of what I just did over the page. the decimal value of it, and that was at T1, and here it comes for T2. I haven't bothered to work it out in exact form for a T2, I just worked it out as a decimal, okay? And there it is, and that's the end of it, okay? So you know now about position, velocity, and acceleration. Yes? You know about vectors, and you know about scalars. We're doing motion in one direction. You know how to do average velocity, you know how to do instantaneous velocity, you know how to do average acceleration, instantaneous acceleration, and you know how to do displacement, and you know how to do distance. If you're not sure, you better go back and have another look at everything that I've showed you today, redo them, and have fun in the process. And we'll see you anon. Okay, all the best.